How dense can you get? That sounds like quite an impolite question. But in this talk, I'm going to argue that in physics, it's a very precise question and it's not so impolite at all. In fact, it's going to lead us into a meditation on what matter behaves like and how it looks as you compress it, as you squeeze it down into smaller and smaller volumes. The story begins with the gentleman in the lower right of this slide. That's a photograph of him. It's actually not him, it's his statue. This is Archimedes. He lived about 2,300 years ago. He lived in a place called Syracuse, which is now, in modern times, the island of Sicily. And he was a very famous astronomer, engineer, mathematician, and what we'd now call a physicist as well. He did many remarkable things, but he's most famous for his solution to a problem given to him by the king of Syracuse. The king had had a crown in gold made for him by a goldsmith, and the king was very suspicious of this goldsmith because he thought that the goldsmith hadn't used all the gold that the king had given. He'd kept some of the gold back for himself, and that he'd mixed in a little bit of silver so that the crown wasn't really made of pure gold after all. And he wanted Archimedes to investigate this. Now, Archimedes was very well able to measure the weight of the crown, but what he couldn't work out was how much space it occupied because, well, it was a crown. It was a very intricate and irregular shape and quite difficult to measure. The solution, as you probably know, is that if you put the crown into a bath of water, then some of the water that overflows the edge of the bath, and it can be collected, and the volume of water which overflows should it be exactly equal to the volume of the crown. And because Archimedes could measure the weight of the crown and could also measure its volume, he was able to work out that in fact the goldsmith had mixed in a bit of silver, so he had been trying to cheat the king. The legend is that Archimedes came on this idea when he was actually in a bath of his own, and he was so excited by the beauty and the simplicity of the solution that he jumped out of the bath and ran down the street yelling, "Eureka!" which means, "I've got it!" And in that single moment became the world's first example of the nutty professor. So, thanks, Archimedes. What we'd say in modern terms is that Archimedes was trying to determine the density of the material which the crown was made of, and that's equal to its mass divided by the volume. The mass is the amount of stuff, and the volume is the space that it occupies. And we all know about it. We know how to measure it. We know it's measured in units of kilograms per litre. And in fact, one way to get your head around this is to know that water has a density of 1 kilogram per litre. So it's actually very convenient to talk, when we talk about other materials, to compare the density with the density of water, and then we only have to give the ratio, which is a pure number. And so in this slide, I'm going to illustrate that idea with just talking about some common substances. On the left-hand side, first of all, you can see there are a couple of gases, helium and air, and they have very small densities. They're very small numbers compared with one, and that matches up with what we know, which is that in general gases are very light. They're not very dense compared with air. And in fact, if you look carefully, you'll see that helium is has a particularly low density. Let's think about a substance we can actually pick up and do things with, wood. The density of wood depends on the kind of tree it comes from. So if you look at pine, for instance, maybe a sample of furniture you've got, that's made from rather low density wood, perhaps 0.4, whereas lignum vitae, that's the densest wood we know of. If you've not heard of it before, it's the wood which bowls are made of. So if anybody in your family goes bowling, they know that when you hold a bowl in your hand, it feels pretty heavy. And that's because the lignum vitae is a very dense substance. We can apply the idea of density not just to solids, but also to liquids. So for instance, alcohol has a density of 0.8. Water has a density of 1, as we've already decided. The interesting thing here is ice, which is the frozen version of water. That's got a density a little bit smaller than 1, 0.92. This is terribly important because it means that ice floats on water. Another piece of physics which Archimedes has bequeathed to us. And the fact that ice floats on water means that water freezes from the top down rather than the bottom up. And that's actually been a very important fact when we consider the evolution of things which swim and life on Earth in general. We can also apply the idea of density to much larger things, such as celestial bodies. We can think about the sun. The sun, we know, is a ball of pretty hot gas. It's mainly hydrogen. There's a bit of helium there. The density of the sun is only 1.4 times the density of water, so it's not particularly dense. And we can compare that with the Earth, which we know, our experience of it is it's a pretty rocky place most of the time. In fact, if you go deep down into the core of the Earth, there's quite a lot of iron and nickel metals. And that means the density of the Earth is significantly higher, 5.5. There are some planets which are much bigger than the Earth, like Saturn, but also much less dense. Saturn is an example of what's called a gas giant, and its density again is less than that of water. On the right-hand side, I'm comparing metals. We very often hear substance statements, in common talking, lead is heavier than aluminium, say. What we actually mean is not that this piece of lead is bigger than this piece of aluminium. What we're actually trying to say is that lead is denser than aluminium. You can see that aluminium is one of the less dense of the metals, whereas lead is one of the denser ones. You've heard of some of the others there, iron, silver. You can see how Archimedes solved the problem because gold is almost twice as dense as silver. So therefore, if you adulterate some gold by adding silver, you're making the resulting object much less dense, and that can be detected. Mercury is interesting. It's a metal. It's also a liquid. And if somebody ever hands you a jar of mercury, it is startlingly heavy. And that's because mercury is really pretty dense. Finally on that list is a metal called osmium. Osmium is the densest chemical element we know of. It's 23 times denser than water. And that's about the only thing I know about osmium. So let's move on. When we, during the course of this talk about different states of matter, it's going to help us to know a little bit about what matter is made up of. Well, you all know that that matter is made of atoms. Atoms are about, well, they're pretty small, 10 to the minus 10 meters across. That means if you hold up a fingernail, there's maybe 100 million atoms going across your fingernail, which is quite a thought. So you're made up of a lot of atoms. And it was thought originally that the atoms, which form the chemical elements, are the most elementary forms of matter. But that's not the case. We know that actually atoms are rather complicated objects. They've got electrons swirling around on the outside, but most of the mass of the atom is contained in a much smaller region at the center. That's called the nucleus, and the nucleus is 10,000 times smaller than the atom, 10 to the minus 14 meters across. And that's really astonishing because it means that most of the mass is actually concentrated in a much, much smaller region than the extent of the atom itself. We also know that nuclei are not elementary objects. They're made up of still smaller things called protons and neutrons. And protons and neutrons turn out to be about 1/10 of the size of a nucleus. They're about 10 to the minus 15 meters across. So that leads to this idea. It's very popular, and it's certainly suggested by this graphic. We sometimes envisage the nucleus as being a bit like a bunch of grapes. Each grape would be either a proton or a neutron. What we've known for perhaps the last 40 years, is that protons and neutrons in their turn are not elementary objects. They're made up of still smaller particles called quarks. And by now it's very reasonable to think, well, is this story going to go on, or does it have an end? And we don't really know, but we've looked now down to scales at least 1,000th of the size of a proton, down to about 10 to the minus 18 meters. And as far as we know, quarks are the smallest, the most fundamental particles that we know of. And that's what we're going to assume during this talk. So, we're talking about matter, we're talking about atoms. How can we organize our knowledge? Those of you who studied chemistry will know that a very good way to do this is something called the periodic table of the elements. Here we list each of the elements, we give it a little square in a table, and they're arranged so that as you go from left to right across the table, the atoms are getting heavier, they're containing more particles, and as you go down the vertical columns, they're called groups, then all of the atoms in those groups have chemically similar properties. And this is the world of chemistry. This is what the universe looks like if you're a chemist. I'm actually going to try to persuade you that the view of the universe seen by a nuclear physicist is at least as interesting. And here it is. This is a plot of all the different nuclei that we know about. And it's a plot on a graph where the distance across horizontally is the number of neutrons in the nucleus, and the distance vertically is the number of protons. So it's possible to find out where some of the nuclei corresponding to the chemical elements we know about are located. Right down in the bottom left-hand corner, there's helium, for instance, with 2 neutrons and 2 protons, and it's got an atomic mass of 4. And we write that little number 4 in the top left-hand corner. A little ways up, there's iron 56, and it turns out that this is a very important nucleus, and most of the iron actually in the world is living very close to the core of the Earth, because as a heavy, dense element, it tends to sink to the bottom of things. And then way out, close to the top, is lead 208 in this case. So there are a total of 82 protons and 126 neutrons in a lead nucleus. It's very important when we write nuclei to always include the mass number at the top left, because it really matters. So for instance, a very good example of this is that as well as there being helium-4, there's another isotope called helium-3. And helium-4 and helium-3, although they have the same chemical symbol, they're really very different substances with very different properties, especially when we cool them down to small enough temperatures that they liquefy. So it's very important in nuclear physics always to quote the mass number. So what do the colours mean? Each of the blue squares on this chart corresponds to a stable nucleus, one that's just sits there and has very predictable properties. Each of the other colours, the orange and the yellow and the pink, correspond to nuclei which aren't stable and tend to decay if left to themselves. And another word for that is radioactive. So the yellow ones are the radioactive nuclei. Now, the way I've arranged them, you can see that all the nuclei we know of fit in this kind of banana-shaped strip going from bottom left to top right. And that begs an obvious question. Why is that? Why do nuclei roughly have the same number of protons as the neutrons? It's not obvious. And in fact, supplementary to that, if we draw a line along which the number of protons is exactly equal to the number of neutrons, you can see that for small nuclei, we start off along that line, but then as the nuclei get larger and larger, going out, say, towards the lead region, we fall below that line. And that means that the heavier nuclei actually tend to have slightly more neutrons than protons. They tend to be slightly more neutron rich. And why is that? It's a complicated question. What makes it interesting is that there is a process by which a neutron can turn into a proton. It can do it by a process called radioactive beta decay. It's possible for a neutron to decay into a positively charged proton, a negatively charged electron, that's the beta particle, and another particle, which is neutral, called an antineutrino. So if you've not come across that before, it's quite important to label it correctly. Now, the point about this is that neutrons are slightly heavier than protons. They're slightly more massive. I'm measuring them in funny units which may not be familiar to you. They're called MeV over c squared. And in those units, neutrons 939.6, protons 938.3. And that means on the whole, this reaction that we've written at the top of the slide here goes from left to right. Because heavier things like to decay into lighter things. That way they release energy. If we had a neutron on its own, isolated, it would therefore decay. The neutron isn't stable. It would decay with a half-life of about 15 minutes. That might leave you feeling a little bit anxious. Aren't all the neutrons in my atoms going to decay? Well, it doesn't happen. Because when the neutron is inside the nucleus, it's actually in a very dense environment. And the rules for how this reaction finds equilibrium change slightly according to density. So under very high densities, particularly if there's a lot of protons around or a lot of electrons, the balance changes and the reaction can actually be suppressed or even go in the opposite direction. Protons can actually, under certain circumstances, decay into neutrons. It's actually quite complicated to understand why that happens, and we need to use a way of thinking called quantum mechanics. We don't really have time to cover quantum mechanics in full detail in this talk, but roughly speaking, when we think about a quantum problem, one of the big features is that a particle can only occupy certain allowed energy states. And I'm going to represent those energy states by boxes. And the boxes here are ordered from left to right. You can think of them as if they were stacked, or they're stacked horizontally. And the boxes on the left-hand side correspond to the lower energy states, and the boxes on the right-hand side correspond to the higher energy states. So when we think about what a quantum system could look like, that can boil down to the question of putting particles, deciding which boxes they can fit into. And at this point, there's a very important physics principle comes into play. There are two different kinds of particle in the world. There are particles called bosons, and bosons have the property that any number of identical bosons can go into the same box. There's no restriction, no limit on how they populate the box. So therefore, it's possible to make systems where all of the bosons live in as low energy as possible, and that's called the ground state. Oh, there's another boson. I want to contrast that with another kind of particle called a fermion, because fermions have to obey the rule that only one fermion can go into any one box. Only one fermion can exist in a particular quantum state. So therefore, when we populate this system of boxes with fermions, they all have to go into different boxes. And if you think about it, that means that some of the fermions have to go into higher energy states. And that's going to cost a bit of energy. In fact, the only way I can save energy is to instead think about different kinds of fermion. Okay, so let's cut to the chase. It turns out that all of the particles we know about that make stuff up, protons, neutrons, electrons, and even quarks, they're all fermions. Whereas the best known example of a boson is a particle of light, a photon. And in fact, this idea that all the photons can exist in the same quantum state, the most commonplace example of that now is when all the photons are in the same quantum state. They all exist in this and that means they're all going in the same direction and they all have the same wavelength. And that gives rise to very, very coherent radiation called laser radiation. So actually, the picture at the top of this slide is some kind of representation of what's going on in a laser. But I'm going to stick to the bottom because I'm more interested in fermions today. If we had a different kind of fermion, it turns out that you can put different fermions in the same quantum state. So I can put a red fermion and a yellow fermion in the same box. The red fermion could be a neutron, the yellow fermion could be a proton, say. And now you can see that one way of lowering the energy of this system is actually if one of the neutrons were to turn into a proton. And then I can actually occupy lower energy boxes and lower the energy of the whole system. And so if we have a reaction like the beta reaction, which can change protons into neutrons or neutrons into protons, it's possible to change the energy of the system to change the balance of protons to neutrons to always find the lowest energy state. So what this next diagram is showing us is how tightly bound various different nuclei are. Some of them are labeled, so the only thing I want to comment is that the most tightly bound nuclei under normal conditions are close to iron. I've labeled there iron 58 and nickel 62. And these, in a sense, are the most stable nuclei under normal circumstances. But as we compress matter, in particular as we increase the density of electrons in the vicinity, it turns out that the balance changes for reasons that we've discussed, and as you go more dense, it turns out that the stable nuclei tend to have still more neutrons in, and they tend to be slightly higher up the banana, if you like. So nuclei such as krypton-84 or strontium-84 would become the most stable nuclei further we go. So this is really starting to think about the question. If we keep compressing matter, if we keep raising the density by squeezing it down, what's it going to look like? Would we end up with all the atoms on top of each other? Well, perhaps not, partly because of the Pauli principle we looked at earlier, which tells us that we can't put too many fermions in the same box. So, what would very dense matter look like? And where would we find it? Actually, a good place to look for dense matter is in the sky. This is a photograph of a bright nearby star called Sirius. You can see it on most winter evenings. The photograph's been taken by a very specialized camera because you can see to the lower left there's a very small, fainter dot. And that's actually a companion of Sirius. It's a star which orbits around it. It's called Sirius B. It's a very special kind of star. It's an example of something called a white dwarf. It's roughly the same mass as the Sun, perhaps a little bit more massive in fact, but it's roughly the size of the Earth. So that means it's much, much denser than the Sun. Remember, the Sun has a density about 1.4 times water. The density of the matter, the material in a white dwarf, is anything between 100 and 1 billion times the density of water. So it turns out that under certain conditions, very, very dense material can be found in stars. And when we think about stars and try to model them, we have to think about what the makeup of the material will be. If we get much beyond about 4 times 10 to the 11, that's 400 billion times the density of water, it turns out that the matter doesn't just consist of nuclei anymore. Actually, things are so dense that it makes sense for some of the neutrons to actually leave the nucleus. We call it dripping out of the nucleus. And that means that the stable form of matter at these very high densities is actually nuclei, but as if they're surrounded by a bath of neutrons. And as you keep raising the density, as you keep going to denser and denser, perhaps closer and closer to the middle of a white dwarf, the proportion of neutrons to nuclei continues to increase. And so by the time you get to 3 times 10 to the 14, Essentially, all the matter is in the form of neutrons, tightly packed together. And it's as if whatever we're talking about now is just one enormous big nucleus. And sometimes we call this state of matter nuclear matter. Remember, the density is 3 times 10 to the 14 denser than water. Under those conditions, the average distance between the neutrons and the protons, well, it's roughly the same size as a neutron or a proton, about 2 times 10 to the minus 15 meters. So we're really talking about a very, very different environment. Is it possible to actually go even denser? And how can that be? What do we have to do to observe densities greater than the densities found inside a nucleus? And the answer, we know, is to wait for a star to explode. So in the photograph is a patch of sky in the southern hemisphere. You need to go to somewhere like Australia to be able to see these particular stars. And this is what it looked like in early 1987, and this is what it looked like a little bit later in 1987. That star at the end of the arrow has actually exploded. It's collapsed in under its own weight. All of its mass has compressed down to a very small region, and then a lot of it has rebounded again to cause an enormous explosion. There's so much energy released in that explosion that for a brief period of time, the star is just about as bright as all the other surrounding stars in the galaxy. And this is a very dramatic event called a supernova explosion. So one way we can study the effects or what very, very dense material looks like is to study supernovae. And here's one I made earlier. This is the remnants of a supernova which happened almost 1,000 years ago. And you can still see these remnants in the night sky. It's in the constellation of Taurus. And you can see that it very much looks like there was a big explosion somewhere close to the middle. If we look right at the middle of that, there is in fact a very faint star. And here's a sequence, taken by a very rapid, clever sequence of photographic exposures. You can see that there's a star at the center, and it's actually fluctuating in brightness in a very regular pattern, and it's flashing on and off about 30 times a second. It's astonishing. It's an example of something that in astronomy is called a pulsar. When pulsars were discovered, they caused quite a lot of bemusement to the astronomers. Didn't know what could be causing this very regular, rapid signal. But it was quickly realized that what it is an example of something called a neutron star. A neutron star is an incredible object. It's roughly the mass of the sun, but it's about 10 kilometers across. That's comparable with the size of Swansea Bay. And the material in a neutron star is truly dense. It's about 10 to the 15 times the density of water. We know of several thousand neutron stars now, and they're very intensely studied objects by astronomers. Here's a cartoon of what the inside of a neutron star may look like. It's got a crust, it's got an atmosphere in fact, and as you go from the outside into the core towards the center, it's getting denser and denser. And actually, you can see at the top of the picture, there's this sequence that we talked about earlier. As we get denser, we start off close to the surface of the star with nuclei bathed, living in some kind of sea of neutrons. But the nuclei are purple, the neutrons are blue in this graphic. By the time you get close to the center of the star, it's like everything is just one big nucleus formed from lots and lots of free neutrons. And indeed, the properties of this matter could well be extremely interesting. I don't really have time to go into it at the moment, but it's still providing huge challenges to physics to understand what's going on. The question I want to keep asking though is that as dense as you can get? Well, maybe not. I want to go right to the heart of things now to talk about the smallest particles that we saw earlier. And they're the quarks. These are the most elementary constituents of matter that we know about. Two of the lightest quarks they have names, they've got rather funny names. One's called up and one's called down. The up quark has got a positive charge, it's 2/3 of the charge on a proton. And the down quark has got a negative charge, it's minus 1/3 times the charge on a proton. And in fact, we can think about the proton as being a collection of three quarks, two ups and a down. If you add up the charges, it's plus 2/3, plus 2/3, minus 1/3, it adds up to 1. If you stand therefore a long way away from the proton, and by a long way away I mean appreciably bigger than its size, which is about 10 to the minus 15 meters, the proton looks like a positively charged particle with charge 1. But if we get close, we can also envisage the proton as being like a little bag containing three quarks, almost rattling around inside. And our picture of the neutron is pretty similar. It's also a bag, but this time inside the bag there are two down quarks and an up quark. And the charges this time add up to minus 1/3, minus 1/3, plus 2/3. They add up to 0. So if you stand a long way away from a neutron, it looks as if it were a neutral particle. So it doesn't look as if it has a charge at all. There's a third quark we can think about. It's called the strange quark. It's like the down quark. It's got a charge of minus 1/3. It's a little bit heavier. So therefore it doesn't form stable particles which we can readily do experiments with under normal conditions. But it's going to become important in what follows. So here's some protons and neutrons. As I said earlier, they're like little bags. They're about 10 to the minus 15 meters across. Each of the bags contains three quarks, and I've represented the quarks as little colored dots in this diagram. And there's a reason for that, but we won't go there today. So what happens if we increase the density of the system? Well, I add more neutrons and more protons, and they'll start to draw them as bags. But after a while, as you increase the density, you have to draw the bags overlapping. When we do this, and we look at the colored dots, after a while it becomes hard to say which quark is in which bag. Does it even make sense to talk about bags anymore? Or should we really be talking about a new form of matter, which is just quarks? Well, this has been a form of matter which has been discussed and thought about for a long time now. Sometimes we call it quark matter. We tend to do that when it's fairly cold. Sometimes we call it quark-gluon plasma, and that's the name we use, the term we use when we're talking about it in its hot form. So, a very big issue, a natural question to ask is, if we go back to the neutron star, it's getting denser and denser as we go from its surface deep into its core. Could there be quark matter at the cores of neutron stars? Well, that's an open question. Nobody actually knows the answer to that. In principle, yes. We think that quark matter will be found eventually, but we also know that neutron stars are quite complicated systems. They're governed by the theory of gravity known as general relativity. And there's a prediction that once they get sufficiently massive, they'll actually swallow themselves up and become a black hole. And it's quite possible that quark matter isn't found in the neutron stars in our universe, because all of the stars which would have been heavy enough to reach those densities have in fact become black holes. So that's an open question. We don't know the answer. But if quark matter were to exist, it's likely to have even more exotic and interesting properties than nuclear matter. It's likely to flow without any resistance. It's likely to conduct electricity and to conduct other properties in a very efficient way. It's potentially even transparent. We may even be able to see through it. All we can do at the moment is study neutron stars to see all sorts of ways in which they behave. All neutron stars spin, as I said earlier, they're spinning very fast, 30 times a second. They're also cooling down because of the radiation they're emitting. And as they spin, they actually occasionally slow down. They also gradually, over time, lose their magnetic field. And by observing those things through the light that we get from the neutron stars, we can actually inform our approach to this question of whether there is quark matter there. There is another theoretical possibility which I can't resist telling you about, and that is that as the quark matter in stars may not just be the up and down quarks, there may also be a significant component of strange quarks in the very densest matter. And it could well be that the resulting strange quark matter is actually more stable than nuclear matter, so that once you form quark matter, it will actually quickly spread out and completely absorb, the whole star would be made of quark matter rather than just its core. And we'd actually be dealing with something called a strange star. If that were the case, if strange quark matter were actually more stable than nuclear matter, it's actually a little bit worrying, because if stars naturally want to be made of quark matter, why wouldn't we? Isn't it if it is ultimately the most stable form of matter, we should worry about it. Well, perhaps we shouldn't worry about it too much, because we're very unlikely to be able to get to those densities in any sort of normal experience. One way in which we could know if strange quark matter were formed is by looking at the size of these very dense stars. Ordinary neutron stars are actually held together under such high densities by the gravitational force due to their weight, due to their mass. And that means there's actually a minimum size. Neutron stars can't be smaller than a particular minimum size. Strange quark stars, on the other hand, they're actually held together by their own cohesion, because strange quark matter is stable. So therefore, in principle, we could find strange lumps of strange quark matter of any size we liked. So if ever astronomers found evidence for there being a star significantly smaller than Swansea Bay, but still behaving in these very crazy ways, that might be evidence for a strange quark star, and that truly would be a very interesting discovery. That is, at the moment, theory and speculation. There are things we can say about quark matter based on experiment, based on things that can actually be done in laboratories on Earth. And the experiments which are done involve colliding nuclei, things like lead nuclei, head-on or close to head-on, but very, very close to the speed of light. I'll say a little bit more about this experiment, but first of all, let me show you a sequence of diagrams to show you roughly what happens. So in the first diagram, you can see a red nucleus rushing in from the left and a blue nucleus rushing in from the right, and they're about to collide. You might think they don't look very much like nuclei. I've drawn them as elongated, and in fact, they're envisaged to be rather flat, a little bit like pancakes crashing together. That's because they're going so close to the speed of light. When objects travel very fast, they undergo something called Lorentz contraction, which means they get shorter in the direction in which they're moving. So nuclei at those speeds don't look like spherical blobs, they look more like pancakes. So this is the moment just before they collide. This next picture is what happens after they collide, and in fact they've moved through each other. The blue guy is now on the left and the red guy is on the right, and they're moving apart. But there's been sufficient collisions between the material of each nuclei that energy has been deposited in what's called the center of momentum frame. And that depositing a large amount of energy into a small region raises the temperature. And it's believed that the temperature in that central region after such a collision could be hot enough to form the quark-gluon plasma. That's what's represented by the thermometer there, the fact that it's very hot. When something very hot is formed, it typically has very high pressure, and therefore it will expand left to its own devices. So immediately after this quark-gluon plasma forms, it expands, and as it expands, it cools. And as it cools, it changes back from the quark state to being now to the particles like protons, neutrons, and other related particles. The collective name is called hadrons. I've called it a hadronic fluid in the diagram, but there can be particles like pi mesons. And then, as time goes by, these hadrons will stream out away from where the collision took place, and they can be detected. And by detecting those particles, we can work out what the conditions were like right at the center. Where do these experiments take place? They take place at particle physics accelerators. The biggest particle accelerator we know of is something called the Large Hadron Collider at CERN. So about 10% of the time, the Large Hadron Collider isn't colliding just protons with each other, which you've probably heard about. It's actually colliding whole nuclei, typically lead. And what I'm showing you here is a diagram of an experiment which has been specially designed to look at those nucleus-nucleus collisions. And these are all the different components. Just like any particle physics accelerator, it's very big and very complicated. Just like any particle physics detector, it's also got a name. It's called ALICE. It stands for a Large Ion Collision Experiment, which is a rather humdrum name, but I prefer ALICE. And to celebrate that, here's Alice herself come to join us. You can see by the scale of the people in this drawing just how big the detector is. Here's an example of one of the particle physics events which Alice has recorded. So you can see it's roughly a barrel shape. Right at the heart of that barrel, at the center, is where the two nuclei collided, and literally thousands of charged particles have streamed away from that region to be detected. They've all had to be detected, recorded, and by looking at not just one collision like that, but many, many millions of such collisions, we can reconstruct and learn more about the conditions which were going on in that initial region when the quark-gluon plasma formed. So let's end by saying a little bit about that medium formed in heavy ion collisions. It's truly a remarkable state of matter. First of all, it's extremely hot. It's 5.5 trillion degrees. When something's 5.5 trillion, it doesn't really matter whether you measure it in Kelvin or degrees centigrade. It's 5.5 trillion. Remember we said when something was that hot, it tends to have a very high pressure, which makes it expand very quickly. Well, the pressure of this medium is 4 times 10 to the 31 times the atmospheric pressure that we're used to here on Earth. Again, these are staggering numbers. Something which I haven't stressed up to now is that within this medium, at these very high temperatures, there's as much matter, there's as much antimatter as matter. The antimatter is made up of things called antiquarks. Again, we don't really have time to talk a lot about antimatter, but it's something that it's worth knowing about. When there's so much energy deposited in a small region by the collision, that it can form both particles and antiparticles. But really, the question we should answer is, how dense is it? 3.5 times 10 to the 16 times the density of water. And for now, that's how dense you can get. This is the densest material that's ever been formed and ever been studied. I can't resist stopping without telling you some of the current mysteries, intriguing questions which these experiments have revealed. One of them is that the medium, the quark-gluon plasma, it was initially conceived of as being a little bit like a gas, but really it's much more like a liquid. And moreover, it's a liquid which flows incredibly easily and well. The property of a liquid which tells you how well it flows is called its viscosity. And one property which both theory and experiment have begun to suggest over the last 10 years or so is that this material which is formed in the heavy ion collision has pound for pound the smallest viscosity of just about any material we know about. In other words, it is the world's most perfect fluid. So, there I think we will leave it. I'd be very happy to answer any questions you might have. You can simply send me an email, but thank you for your attention and keep watching the skies.